We arrive now to the Copernican revolution, the time that recent philosophers of science call a paradigm shift. Astronomy had been dominated by the view that the Earth was the center of the universe. Then Copernicus came and said, what if the sun is the center of the universe? The Earth would be included among the other planets, and they would all orbit the sun in circles. At the time that Copernicus was hesitantly presenting this idea, people thought it was interesting. But it, but people were slow to accept it because it went against common sense. Let's delve now into the late 15th century and early 16th century, the time of Copernicus, and see what it was like. That was the time of the Renaissance. Western Europe was bringing back ancient Greek and Roman art, which included painting, sculpture, and architecture. So what about science too? And this is where Copernicus jumps into the story. Nicolaus Copernicus was Polish. His father died when he was about 10, so his uncle Lucas, the brother of his mother, saw to it that Copernicus received a university education. Lucas became Prince Bishop of Varmia in 1489, and around that time, he sent Copernicus away to the University of Krakow. In Krakow, Copernicus studied the arts, but he probably studied astronomy outside the university. Copernicus was there for 4 years, but left without getting his degree because a position opened up in the Varmia canonry under his uncle. But his installation to that position was delayed, so his uncle sent him to Bologna, Italy, to study canon law. But he also studied humanities and astronomy while he was there. He became an assistant to the famous astronomer Domenico Maria Novara da Ferrara. He developed new ideas reading the Epitome of the Almagest by Georg von Feuerbach and Regiomontanus. He observed a 1497 lunar occultation of Aldebaran. That means the moon went right in front of the star Aldebaran and hid it, occulted it. That's why it's called an occultation. And he observed this to verify some peculiarities about lunar motion from the Epitome of the Almagest that he had been reading. And that got him even more interested, and he started reading many Greek and Latin authors on astronomy. After spending the Jubilee year 1500 in Rome, and then a trip back to Varmia, Copernicus returned to Italy to finish up his canon law doctorate in Bologna and to study medicine in Padua. In 1503, he returned to Varmia and spent the remaining 40 years of his life in that area. He started out as his uncle's secretary and physician, but he later took on administrative and economic duties. He even wrote some works on monetary theory. But let's get to his astronomy. Sometime in between the years 1510 and 1514, he wrote what is now called the Commentariolus, the Little Commentary. In this we can see that early on he already thought the sun was the center. There were some things he would still tweak between the Commentariolus and the De Revolutionibus Orbium Celestium, but the foundation was present already. In the Commentariolus, he started with 7 basic assumptions. First, there is no one center of all the celestial spheres. Second, the center of the Earth is not the center of the universe, but only the center toward which heavy bodies move, and the center of the moon's orbit. Third, all the spheres surround the sun as if it were in the middle of them all, and thus the sun is at least near the center of the universe. Fourth, the ratio between the distance between the Earth and the Sun and the distance between the Earth and the fixed stars is so small, much smaller compared to the ratio of the radius of the Earth to the distance from the Earth to the Sun, that the Earth-Sun distance is imperceptible compared to the distance to the fixed stars. Fifth, any apparent motion in the fixed stars arises from the Earth's motion. The Earth completes a daily rotation on its axis, while the fixed stars are unchanged. Sixth, the apparent motion of the Sun arises from the Earth's motion. The Earth orbits the Sun like any other planet. Thus, the Earth has more than one motion. It has its daily rotation, but also its annual revolution around the Sun. And seventh, the apparent retrograde motion of the planets is also due to the Earth's motion. For the outer planets, it's when the Earth is passing them up in its orbit. The motion of the Earth alone thus suffices to explain many inequalities in the heavens. The Commentariolus was not published widely, but it is proof that Copernicus held the heliocentric theory from early on in his life. Copernicus then made dedicated observations of the planets and the Sun. He would observe eclipses with other astronomers. Copernicus used a quadrant, a triquetrum, which is pictured in this slide, and could measure angles more accurately than an astrolabe. And he also used an armillary sphere. He discovered the variability of the Earth's eccentricity. And here, remember that he didn't think that Earth's orbit was elliptical. He thought it was circular. So eccentricity does not refer to describing the ellipse, but rather that the circle was off-centered. But he did think that the Earth orbited the Sun, so this could mean that the Sun is off-center. He also discovered some movement of the solar apogee in relation to the fixed stars. Let's take a step back now and recall what is going on in Western Europe at this time. At this time were some councils calling for a reform of the Julian calendar. St. Peter's Basilica was being built in Rome, and there were some abuses of indulgences, and part of that led to Martin Luther posting his 95 Theses in 1517. So this was all happening right around the time that Copernicus was making these more detailed observations, refining his theory. Some of Copernicus's close friends became Protestant, but he never seemed to show any tendency in that direction. Copernicus was pretty much finished with his work, De Revolutionibus Orbium Celestium, by about 1532. But he didn't want to publish it because he feared criticism. He was going against a centuries-old idea that the Earth was stationary at the center of the universe. He didn't keep it entirely a secret, though, and rumors of his ideas interested many people. In 1539, Georg Joachim Rheticus went to Copernicus and became his pupil for 2 years. Rheticus published a summary of the heliocentric theory, and Copernicus saw that it got a positive reception. So that helped convince Copernicus to have his work printed. At first, Rheticus took charge of the task of printing, but then handed this task over to the Lutheran Andreas Osiander, who saw it to completion. Copernicus was old at this time and became paralyzed. While he was on his deathbed, Andreas Osiander added an unauthorized and unsigned preface to the work, saying that it was just a mathematical hypothesis that need not be true. Just a way to simplify the calculations to find the planet's positions. It is told that Copernicus was given a printed copy of his work on his deathbed, and after he saw it, was able to die in peace. But he never saw this preface from Osiander. Perhaps it was because of this preface that it didn't stir a lot of controversy right at that time. The whole controversy did not really come out until the time of Galileo, which we will talk about next week. Rheticus could have been the successor to Copernicus, but he was more interested in developing trigonometry and teaching math. He just never rose to the occasion. Another astronomer, Erasmus Reinhold, could have been the successor to Copernicus. In 1551, Reinhold published the Prussian tables, astronomical tables that were based off of Copernicus's work. But Reinhold died prematurely just a couple years later. Heliocentrism would be slow to catch on, and the next big astronomer would not even hold heliocentrism. Tycho Brahe had a compromise system. Heliocentrism would be slow to catch on, and the next great astronomer, Tycho Brahe, was not even convinced by it. 3 years after the death of Copernicus, Tycho Brahe was born. Tycho was from a Danish noble family. He was the oldest in his large family, and for some reasons that are not known, he was the only child of his family that was raised not by his parents, but by his uncle Jorgen and aunt Inger Oxe instead. He attended Latin school from ages 6 to 12, and then attended the University of Copenhagen at age 12 to study law. But he also studied other subjects, including astronomy. He saw the solar eclipse of August 21st, 1560, which was predicted, but it was 1 day off. This interested him, and he began to read more astronomy books, including works from John of Sacrobosco, Peter Apian, and Regiomontanus. At age 15, he began studying at the Lutheran Leipzig University. In 1563, he observed the conjunction between Jupiter and Saturn, but the predictions from both the Copernican and the Ptolemaic tables were inaccurate. That's when Tycho decided that astronomy needed more accurate observations, and that's one thing he would accomplish with his life. At this time, Denmark was at war with Sweden. In 1565, his uncle Jorgen died, and Tycho returned to Denmark. Then the following year, 1566, Tycho began studies of medicine at the University of Rostock. One day, he was at a professor's engagement party, and he got into a drunken quarrel with his third cousin over who was better at math. A couple weeks later, they decided to resolve their feud with a duel in the dark with swords. And in this duel, Tycho lost the bridge of his nose and got a large scar on his forehead. He would afterwards wear a prosthetic nose made of brass. At the time, it was said to be of silver or gold, but his body was dug up recently, and the evidence is that it was brass. The next year, in 1567, Tycho returned home and decided to dedicate himself to astrology. Then he traveled to different cities, started building quadrants and observatories. In 1570, his father fell ill, so Tycho returned home until his father's death in 1571. King Frederick II then proposed to him that a superior observatory be built. This would be Uraniborg on the island of Hven, which is in between Denmark and Sweden. In 1571, Tycho fell in love with a commoner, Kirsten, whom he marries not formally, but by morganatic marriage, since they were of unequal social rank. and many family members disagreed with the decision. They remained married until Tycho's death. In 1572, there was a supernova in Cassiopeia. Nova meaning a new star. And Tycho wrote De Nova Stella in 1573, refuting the Aristotelian claim that what's in the heavens beyond the moon doesn't change. The image on this slide is a recent X-ray picture of Tycho's supernova. The supernova didn't have the parallax to be sublunar. He showed also that comets must be beyond the moon. Tycho continued doing astronomy and traveling. In 1576, construction began for Uraniborg. He built larger and more accurate quadrants and sextants, and was thus able to make more accurate observations than anyone before. His accuracy approached 1 arcminute. Remember when you are outside and you extend your arm and your little finger covers up about 1 degree? So a 60th of that would be 1 arcminute. So that was the accuracy that Tycho was approaching in his observations. And that's impressive without a telescope. That year also, Tycho published the first tables for corrections due to atmospheric refraction. The fact that light bends a little bit in our atmosphere, and that depends on the angle it hits the atmosphere at. In 1577 and 78, he observed a great comet and measured that it was beyond the moon. He also realized that the comet's tail is always pointing away from the sun. During these observations of the comet, Tycho was inspired to develop an alternative Copernican model in which the Earth was immobile. Some of the reasons for that were Copernican predictions had just as much error as Ptolemaic predictions. In this model, Tycho eliminated the crystalline spheres. He was the first to do away with those. He just thought the Earth was too sluggish to be in constant motion, and he argued from parallax that the Earth couldn't orbit the sun. He couldn't detect parallax in any stars. And he wouldn't have been able to with the instruments he had. Friedrich Bessel would be the first to observe parallax in a star in 1838, so a couple of centuries later, with the star 61 Cygni. And he measured a parallax of 0.314 arcseconds. So that's about 200 times smaller than the limits of Tycho's observations. He also argued that if the stars are really far away, so that we don't observe parallax, then they'd have to be really large, like larger than the sun, larger than the orbit of either the Earth or the sun, depending on which model you want to adopt. Tycho's model also had the orbits of the sun and Mars intersect. This made his model different from other geo-heliocentric models, that is, models in which the Earth is stationary, the sun orbits the Earth, but other things orbit the sun. We saw one example of this with Marcianus Capella, who just had Mercury and Venus orbiting the sun. In 1581, a second observatory underground at the nearby Stjerneborg was constructed because the instruments at Uraniborg were exposed to the elements and the movement of the building. Tycho would also practice alchemy at Stjerneborg. For the next 20 years, Tycho ran Uraniborg and Stjerneborg as a research institution with about 100 students and artisans. Uraniborg had its own printing press and paper mill. Tycho continued to serve as a royal astrologer and had to present an annual almanac to the court. In 1588, Tycho's 2-volume Introduction to the New Astronomy was published. Also that year, Frederick II died, and his son Christian IV was only 11 years old, so a council would rule until 1596. Tycho was not on the best terms with this council, and so in the following years, Tycho was less and less appreciated. He carried on his observations and completed a star catalog with the positions of 1,000 stars. Then in 1597, after some disagreements with Christian IV, who had now come into rule, Tycho went into exile. In 1598, he published a work describing the instruments he had used in Uraniborg and Stjerneborg. In 1599, the Holy Roman Emperor Rudolf II invited him to Prague, where he became the official imperial astronomer, and there his wife and children were finally treated like nobility. Tycho built an observatory about 45 kilometers northeast of Prague, and that's where he met Johannes Kepler. Now, he had already invited Kepler by letter to Uraniborg years before. Kepler did not go there then, but once Tycho was at his observatory near Prague, Kepler went and served as Tycho's assistant starting in 1600. Together, they worked on a new star catalog, which became the Rudolphine tables, named after Rudolf II. Kepler tried to persuade Tycho to accept Copernicus's heliocentric theory. One day in 1601, Tycho attended a banquet and refused to relieve himself because it would be a breach of etiquette. Tycho contracted a bladder or kidney ailment and died 11 days later. The next year, Kepler published Tycho's lunar theory posthumously. Tycho had discovered a variation in the moon's longitude and librations in the inclination of the moon's orbit relative to the ecliptic. Tycho left a great legacy, and fortunately, his successor, Johannes Kepler, was able to push new frontiers in astronomy. Johannes Kepler was born in what is now Germany. His father, a mercenary, left the family when he was 5. His mother was a healer and an herbalist. Kepler observed the Great Comet of 1577 when he was 6 years old, and then he observed a lunar eclipse when he was 9. These motivated him to study the subject of astronomy. But childhood smallpox left him with crippled hands and a weak vision, so he was no longer able to see the stars. For this reason, he turned more to theory rather than observation. He went through grammar school, Latin school, and seminary, then went to the University of Tübingen and studied philosophy, theology, mathematics, and astronomy. He was taught both the Ptolemaic system and the Copernican system. He became a defender of heliocentrism, using both theoretical and theological arguments. In 1594, he became the professor of mathematics and astronomy at Graz. In Graz, in 1596, he published his first major astronomical work, Mysterium Cosmographicum. This work defended the Copernican system. One chapter was dedicated to reconciling heliocentrism with biblical passages that seemed to support geocentrism, but the University of Tübingen asked him to remove this chapter in order to publish the work. Kepler thought he had discovered God's geometrical plan for the universe. He considered the universe itself as an image of God, with the sun, S-U-N, corresponding to God the Father, with the fixed stars corresponding to God the Son, and with the space between corresponding to the Holy Spirit. He came up with the idea that each of the 5 Platonic solids could be between the planetary orbits. He had the octahedron between Mercury and Venus, the icosahedron between Venus and Earth, the dodecahedron between Earth and Mars, the tetrahedron between Mars and Jupiter, and the cube between Jupiter and Saturn. He found a formula relating the size of each orb to the period of each planet's orbit, but he later rejected this formula because it wasn't precise enough. Copies of this work, Mysterium Cosmographicum, were sent to prominent astronomers, and Kepler became established as a highly skilled astronomer. This work represents the first step in cleansing the Copernican system of the remnants of the Ptolemaic system that were still clinging to it. In 1597, Kepler married Barbara Müller. They would later have 5 children, the latter 3 of whom survived infancy. Around that time, Kepler and Tycho Brahe began exchanging letters, and Tycho took issue with Kepler's use of inaccurate numerical data. So then in 1600, Kepler goes to Prague to work as Tycho's assistant. He started out analyzing Tycho's observations of Mars, but Tycho would not let Kepler copy any of his own data. They later made a formal contract for Kepler's position, and Kepler went to Graz to get his family. Kepler's new project under Tycho was to develop the Rudolphine tables in order to replace the Prussian tables, which had been developed in 1551. The Rudolphine tables would not be completed until 1623 and then published in 1627. When Tycho died unexpectedly, Kepler became his successor as imperial mathematician for Rudolf II, and he finally had access to Tycho's data. In 1604, Kepler published Astronomiae pars optica, the optical part of astronomy. This covered the inverse square law for the intensity of light, reflection by flat and curved mirrors, principles of pinhole cameras, parallax, and the human eye. Kepler was the first one to recognize that images are projected inverted and reversed by the eye's lens onto the retina. In 1604, there was another supernova, and many astrological interpretations were circulating about it, but Kepler was skeptical of those. He noted the fading luminosity of the supernova and argued that it must be in the sphere of fixed stars since no parallax was observed. In 1604, he also wrote Astronomia Nova, New Astronomy. It wouldn't be published until 1609 due to legal disputes of using Tycho's data. But the Astronomia Nova included the first 2 laws of planetary motion. It took a lot of work to come up with these. Kepler had attempted 40 different ways to fit Mars's orbit, mostly with ovals, but then he tried an ellipse. This leads us to Kepler's first law of planetary motion. All planets move in elliptical orbits with the sun at one focus. And Kepler's second law was that planets sweep out equal areas in equal times. We'll come back to his third law. Kepler had not arrived at that one yet. 1609 and 1610 were big years for astronomy, with Galileo's use of the telescope. Kepler made and published his own telescopic observations of the moons of Jupiter. Galileo didn't pay much attention to Kepler, but we'll talk about Galileo next time. In 1611, Kepler published a work, Dioptrice, a theoretical basis for optics concepts and how to combine lenses for a Galilean telescope, as well as an improved telescope, the Keplerian telescope, which had higher magnification. Also in 1611, Rudolf II abdicated. Kepler's family got smallpox. His 6-year-old son died. And Kepler then arranged to move to Linz, Austria, and teach there. But before that could happen, his wife Barbara got sick and died, and then Rudolf died in 1612. Matthias, the new Holy Roman Emperor, reaffirmed Kepler's position as imperial mathematician, but allowed him to move to Linz. So the move to Linz then happened in 1612. In 1613, Kepler published De Vero Anno, a treatise on the year of Christ's birth, and Nova Stereometria Doliorum Vinariorum, on measuring the volume of containers, a mathematics work. In 1613, Kepler also got married again to Susanna Roettinger, with whom he had 6 children, 3 of whom survived into adulthood. From 1615 to 1621, Kepler's own astronomy textbook, The Epitome of Copernican Astronomy, was published in 3 volumes that came out gradually. This work contained all 3 laws of planetary motion, and Kepler attempted to explain celestial motions through physical causes. Let's take a look now at Kepler's 3rd law. Kepler's 3rd law is mathematical. The ratio of the square of an object's orbital period with the cube of the semi-major axis of its orbit is the same for all objects orbiting the same primary. Here, primary means the most massive. So in the case of our solar system, it's the sun. When we're in class together, we'll practice applying this 3rd law. In 1617, Kepler's mother was accused of witchcraft, and she was later imprisoned. So Kepler went to help defend her and eventually got her released in 1621. During that time, he was working on Harmonices Mundi, the harmony of the world. In this work, he attempted to explain the proportions of the natural world in terms of music. Kepler's 3rd law also appears in The Harmony of the World, and we know the date he came up with it, March 8th, 1618, but we don't know exactly his reasoning, how he came up with it. In 1626, Kepler moved to Ulm because Linz was besieged, and he arranged at his own expense for his Rudolphine tables to be printed. He traveled around during his last years and fell sick and died in 1630. Although Kepler was ignored by Galileo and Descartes, his Epitome of Copernican Astronomy became the most widely used astronomy textbook from 1630 to 1650. Kepler would be appreciated much more once Isaac Newton derived Kepler's laws of planetary motion from his force-based theory of universal gravitation. Now that we've brought up Kepler's laws, it's good for us to know a little bit about how we understand orbits today. Most orbits are elliptical. They could also be parabolic or hyperbolic, but parabolic and hyperbolic orbits are one-way trips, so we'll focus on elliptical orbits. The ellipse in red has 2 foci, and the sun is at 1 focus. From any point on the ellipse, if you add the distance to each focus, it is the same, and it's equal to the major axis, 2a. The semi-major axis, a, is half of the major axis, and the semi-major axis is the first orbital element we use to describe orbits. It tells us how large they are. But of course, the semi-major axis is not enough. Some orbits can be more circular than others. So we want to know the eccentricity of the ellipse as well. To get the eccentricity, we need to know the semi-minor axis, which is at right angles to the semi-major axis. To get the eccentricity, we take the square root, that's the half power, of 1 minus the square of the ratio between the semi-minor axis and the semi-major axis. For a circle, the semi-minor axis is equal to the semi-major axis. They're just both radii of the circle, so their ratio is 1. So we get a 1 minus 1 squared. 1 squared is 1. 1 minus 1 is 0. Square root of 0 is still 0. So the eccentricity of a circle is 0. The eccentricity of a parabola is 1. So the eccentricity of an ellipse is a number between 0 and 1. As a planet moves on its elliptical orbit, there are times when it's closer to the sun and times when it's further away from the sun. The closest point to the sun is called perihelion or periaps or pericenter, and the point at which it's furthest from the sun is called aphelion or apoaps or apocenter. This image depicts a planar orbit that we're sort of looking down on, but orbits can also be inclined at different angles. So inclination is another orbital element. In total, there are 6 numbers we use to describe orbits. Here I've shown you semi-major axis, eccentricity, and I've described inclination. There's also the mean longitude. You could think of that as the angle, like where the planet is at in its orbit at the time. There's the angle telling us where pericenter is, so the longitude of pericenter. And there's also longitude of the ascending node, and that's for inclined orbits. It tells us, all right, at what place in its orbit does the planet go from being below the reference plane to above the reference plane. Orbits in 3D can be complicated, so we'll focus on 2D orbits. So with Copernicus, Tycho, and Kepler, we have stepped into a new era for astronomy, a new era for science in general. This is often called the scientific revolution or the Copernican revolution, and it had profound philosophical implications. If the Earth isn't in the center of the universe, what does that mean for mankind?